reactant. It's just a little algebra game. If I have K1 times the concentration of NO times the concentration of Br2 set equal to K negative 1 NOBr2. I want to solve for NOBr2 in terms of the initial reactant so I can sub that into this observed rate law. So let's just divide both sides by K negative 1. So that simplifies. And the concentration of NOBr2 is the same as saying NO first order, Br2 first order. Taking these concentrations and subbing them in to that intermediate, this is what we'll get. Subbing that relationship in, and this was my algebra right here, I solved for NOBr2. If I sub in the initial thing we solved for, remember how we started, rate is equal to K times the intermediate NOBr2 times the concentration of NO. That's just taking our slowest step and writing that as its rate determining step. The rate determines from the slow step. So that's just rewriting this down here. We want to get rid of this NOBr2 because it's an intermediate. The process we used was subbing in what is the equivalent value for NOBr2 in terms of the original reactants. I'll write that here. Rate is equal to K, and instead of writing NOBr2, we'll write what we solved for, NO and Br2. And remember, we still have another bracket over here of NO, so I'll just make that with second order with respect to NO. This, my friends, does indeed match the observed rate law from this particular equation. We knew that a termolecular collision was not likely. We were trying to develop a reaction mechanism that got us second order with respect to NO, first order with respect to Br2, but using a multi-step mechanism. When I realized the overall rate law, the observed rate law is termolecular, I know the first step cannot be the slowest step. The slowest step gives me the rate law. That's not the observed rate law from that proposed mechanism. So I chose to make the first step faster and the second step slower, then simply subbing in the equivalent values for the intermediate. So in general, whenever a fast step precedes a slow step, we solve for the concentration of the intermediate by simply assuming that the equilibrium is established in that fast step. In other words, just think of this as an equal sign. Forward and reverse are an equal value. I write the rate law for the forward, set it equal to the rate law for the reverse, pulling out the NOBr2 intermediate and seeing what it's equal to. Let's take a peek at a next example. Show that the following mechanism for the reaction 2 NOs plus Br2 yields 2 NOBr also produces a rate law consistent with the experimentally observed one. So let's take a peek. The experimentally observed rate law, we just worked this. Rate is equal to K times the concentration of NO second order, Br2 to the first order. That's just borrowing that same example up above. Do you remember we had a choice to make? We had 3 overall molecules. We had molecule of Br2 and a molecule of NO and a molecule of NO. We realized that all 3 won't collide at once. It could not be a termolecular. We had a choice to make. Do I want to hit NO and Br2 in my first mechanism? That's what we did first. But another equally lovely choice was to just collide the like molecules in the first step and use the bromine in the next step. That's what this proposition of a mechanism looks like. So we're trying the alternate pathway. Either way is going to get us to the same place. So a second proposed mechanism says, let's take the like molecules and collide those. Then in the next step, take that intermediate and bombard it with the bromine, so that each one of these steps would be a bimolecular elementary reaction. When I look at my proposed step, NO plus NO is a bimolecular collision. It does not give me the observed rate law, so I know that that has to be a fast step. The observed rate law would match if it were a slow step. In the next step, that intermediate that was produced then gets consumed by hitting it with that third molecule of bromine. 2 units of NOBr would be the slow step. The rate law comes from the slowest step, so this is what we know so far in our observed rate law. Rate is equal to K times the concentration of N2O2 times the concentration of Br2. The observed rate law comes from the slow step. The problem is N2O2 is an intermediate, and we're not allowed to have an intermediate in an observed rate law. We need to sub in some equivalent value for the intermediate N2O2. We go back to that first step. Here's what we know. That the forward reaction K1 times the concentration of NO and it's colliding with itself, so that would be a second order with respect to NO. That's equal to the reverse reaction in a dynamic equilibrium, which gives the K negative 1 times the concentration of N2O2, and that's with first order with respect to the N2O2. I want to know what can I place in as an equivalent value for this intermediate in terms of the original reactants. So I can see to get this by itself, it's a simple division of the K constants. That in other words, N2O2 can be equal to NO to the second power. So this right here simplifies the equation of the N2O2. So let's just rewrite what we figured out. Rate is equal to K, and now instead of writing N2O2, let's sub in the equivalent amount of the initial reactants, NO to the second order, and we still have that Br2 from the slow step, which is all right to have there because it is in the observed rate law. Notice that this pathway also matches the observed rate law. Friends, we decided it wouldn't matter. We've got the same place. If these 3 molecules have to go and collide somehow, we get the same answer if we choose to collide 2 like molecules and then a second collision. Or, as in the first job, we took a like molecule of NO and Br2, collided that, and then used the third one. So both pathways got us the same observed rate law. Try this. The first step of a mechanism involving the reaction of bromine is this. Bromine molecule forms 2 bromine atoms. It says it's fast. It's in equilibrium. What is the expression relating the concentration of Br to that of Br2? Here's what we know. The forward reaction would have rate is equal to K times the concentration of Br2. That would be equal to K negative 1, where the atom of bromine